you're a speaker, can you raise your hand? I guess Zichong Wang and Andrew Estorno and Brianna Richardson. Good. And Catherine Cacho and Jose Alvarez. Great, cool. Sorry, there was another thing I got assigned this morning that I forgot about this. All right, welcome to the session on practical methods, and we're going to start right now. And the first presentation is on his actually best award paper. There should be a certificate, actually. Okay, I'll find you that later. But let's congratulate Zichong Wang on the best paper award, and Zichong, welcome to the stage and give him some.
Okay, good afternoon, everyone. I'm Zichong Wang. I'm very thrilled to be here today to present our research, prevention discriminatory decision-making in evolving data streams. In our fast-paced, data-driven world, decisions that significantly impact individuals and communities are increasingly be automated. Those decisions are often increasingly based on the machine learning model trained on large dynamic dataset, or what we commonly refer to as data streams. However, as existing as those advances may be, they also bring significant challenges, especially in ensuring fairness and avoiding discrimination. Traditional fairness model in machine learning often promise on static dataset, finding themselves struggling in fairness in the face of constantly evolving data streams that power many of our competitive systems. Indeed, as those data streams evolve over time, the fairness of our model's prediction can shift, potentially leading to bias or discrimination outcomes. This issue forms the cornerstone of our research. And here is again for my research today. Before we drive further, let's define what we mean by data stream. In the simplest term, the data stream is referred to a sequence of data that continues generate over time, probably infinite, and each item have a time step. Unlike the static dataset, the data streams deliver data in real time, and the information is often processed and analyzed as it arrives. And we have two examples in here. First, healthcare. Consider hypothermia scenario where a predictive model trained on data streams suggests that a patient with black skin are less likely to require intensive care. Such a potential indicate bias within the model and could lead to serious disparity in care. And the second example is the finance service. Think about a bank and a financial institution. The bank and financial institution may use data streams to monitor the loan or credit card approval. For instance, if a loan approval system trained on data streams and start to unfairly reject application from some certain zip code or based on certain demographically attribute, it's become imperative to apply fairness check. And why should we abstract the data as data streams? There are two reasons. One, you can't store all the data. Think about the high frequency stock market or the social media. Both applications can generate a million of data in 1 minute, so it's impossible to store all the data. Even if you can, it's very expensive. The second is when you don't want to store all the data. A great example is COVID-19. COVID-19 does not exist 5 years ago. So if we use the prediction based on like 5 years ago data, we might miss the key insight and turn about on the recent development. And we can compare offline model and online model. In the offline model, a machine learning model is trained on a fixed dataset. The dataset is gathered before the training process begins and won't change during the training process. Once the model is trained on the dataset, they can prediction on new data point. But the model does not change or adapt based on the new prediction. On the other hand, for the online model deals with the data point sequentially as they arrive. The model are continuously updated and trained on those new data points. The output is not just a trainable model, it's training the model is a trainable model, so it can continue evolve and adapt to new data. And this is the three main challenges focused on our research. Traditionally, most fairness notation in machine learning have been designed with the assumption for static dataset. So how can we evaluation fairness evaluation in the streaming dataset? So we introduction the continuous static parse different. For here, the f is the prediction function and d is the data point. The s denotes the sensitive attribute and y is ground truth. And t is the correct time the static parse difference, and t minus 1 is not the difference at the previous time point. The decay factor lambda, which lies between 0 and 1, is used to regulate and the amount of influence of previous time point on the current fairness evaluation. A high value of lambda gives more weight to the past, while a low value makes the measure more sensitive to recent data point. One of the critical aspects we need to consider in our fairness evaluation is the concept of fairness boundary utilities. This allows us to understand and manage the trade-off between fairness and performance, providing a uniform metrics that we can use to across and improve our models. Here is an example. For first model, the performance is increased by 1% and the fairness decreased by 1%. The second one is opposite, which the performance decreased by 1% and the fairness increased by 1%. So it's very hard to say which one is better. For this case, we can use FBU, which includes 5 effectiveness level like the sides show. And we can explain in this picture, as we can say, the main idea back for FBU is if everyone receives same result, then the model is fair because it treats everyone similarly. So we can say the red line represents fairness and the blue line represents the performance. The M100 means we use one label to replace all outcomes, prediction outcomes, so everyone receives same result. That's why it has the highest fairness and the lowest performance. And we have total 11 points, which is the original model output, and we replace with 10% outcomes and 20% outcome and until to 100% outcomes. And based on those 11 points, we build the baseline. It's the yellow line in the figure B, and the x-axis is the fairness matrix value, and the y-axis is performance matrix value. We can use accuracy or static parity difference. So the 1 to 5 is corresponding to the 5 level, which I showed in the last slides. It's important to compare two models. In this case, the M1 is better than M2 because M1 have a larger area than M2, sorry. And in our approach to deal with both concept and fairness draft, we employ an algorithm as known as adapt windows. And we also implement synthetic models fairness where smooth. And for Adwins, we set two thresholds. One is performance, one is fairness. Those thresholds help to configure two levels of error direction, a warning level and a change level. The warning level is identified by multiple theta by 10, result in a lower value. This means we hit the warning level before the change level. And once it's in a change level, we use oversampling technique to rebalance data streams. Existing oversampling technique got limitation. For example, the RS is a random oversampling. After we apply the random oversamplings, the difference between privileged group and unprivileged group actually is increased, which causes more bias. And that's why we don't directly use SMOT. As in this showing, like in left, we try to generate the triangle symbols. But actually, we can say the new triangle symbol is fill into the blue circle area, so which causes more bias. So in our work, we adopt a nuanced approach to handle imbalance in our data. First, we perform clustering operation in our data. This helps us to identify similar samples and group them together. Second, we apply the filtering step to the silhouette score, which we cut the sample close to the decision bordering. And finally, after establish our clustering and ensure the quality, we run the smarter algorithm within each cluster to generate synthetic majority samples. And this is the result for our approach. We can say our approach achieves best fairness and while maintaining the performance. And this is the result for FBU. We can get the same conclusion like the table we get. And that's the end of my presentation. Thank you for listening.
Do you have other authors?
No,
Okay, all right. So I guess, well, congratulations again. And this paper got a Best Paper Award. And as other, I guess. No. As in other sessions, we're going to QA at the end. So the next author is Andrew. I guess. I guess you can do it. Thank you.
All right. Hello, everyone. I'm Andrew Esternell. I'm going to be presenting the paper Group Fair Classification with Strategic Agents. This is a joint work with my co-authors listed here. So before we start talking about group fairness and how strategic agent behavior plays a role in this, let's just kind of start by defining these things with a motivating example. So in the types of problems that we look at in this paper, we can think of these through the example of lending, in which we have applicants. They submit applications to a bank. This is just the data that's going to the bank. The bank then uses some type of algorithmic decision-making process to make a binary decision, approve or deny. And here, being approved is more desirable than being denied. And typically in these kinds of systems, we're imposing some type of group fairness. And just as an example, maybe we want to have the percentage of blue applicants and the percentage of green applicants be roughly equivalent. This would effectively be bounding demographic parity. More generally, right, we just have this unfairness metric that's a function of the model, the features X, the labels Y, and the group G. And so within this, it might be the case that the bank, for either kind of regulatory reasons, moral reasons, whatever, needs to minimize loss subject to this fairness metric. And typically what's happening is that these kind of fair models are replacing what we might call fairness agnostic models. So it might be the case that the bank is using some fairness agnostic model that doesn't have this fairness constraint, and then the bank now, for whatever reason, has to come in and use a fairness-aware model. And so in this paper, what we're interested in is asking, how does strategic agent behavior affect the relative fairness between these two models? And in particular, what we'll look at is cases in which strategic agent behavior actually leads to the fair model being less fair than this fairness agnostic model. And this kind of strategic agent behavior, we kind of haven't defined what that means yet, but we'll look at it next. But effectively, as we said, being approved here is better than being denied. It's desirable, and so it might be the case that agents engage in manipulations in order to get approved. And so we'll look at the kind of strategic agent behavior side of this next, but really the observation that we're looking at throughout this paper is, how does strategic agent behavior impact fair learning algorithms? And so in strategic agent behavior, right, it might be the case that we have an applicant who has these true features, and they know that if they submit this application to the bank, they are likely to get denied. So rather than submitting and getting denied, they falsify or manipulate their data. So here we see that they're over-reporting their assets, they're under-reporting their debt, and we're studying this strategic behavior in terms of pure manipulations, meaning that it isn't that this agent is going out and acquiring more assets or paying off debt. These are pure manipulations, and they're not changing the underlying true label of the agent, meaning in this case, they're not changing the credit worthiness of the agent. And more formally, we can define a manipulation saying that an agent with true features X, where f of x equals 0, meaning that this agent would be denied for a loan, they have optimal manipulation here, which is simply minimizing some manipulation cost subject to being positively classified. And what we'll say is that an agent will manipulate if this optimal, if the cost of their optimal manipulation is less than some budget B. So here we're modeling agents as being able to manipulate within some cost, and if they have an optimal manipulation within that cost, they will take that manipulation. And in the paper, we study these kind of two common manipulation cost functions, which are probably the two most common found across the strategic classification literature. And in this paper, we introduced the notion of a fairness reversal. And so a fairness reversal is occurring between the fairness agnostic model, FC, and the fairness aware model, FF, if strategic agent behavior, meaning that the agents are manipulating in order to get a better outcome, is causing the fair model to become less fair than the conventional model. And so we see here that, in a way, almost the functionality of the fair model is swapping with the conventional model, where the fact that you induced these fairness constraints and then agents behave strategically, you actually would have been better off if you had just used the fairness unaware model. And we'll just kind of begin by looking at an empirical example of this. So what we have here is on the y-axis, we have positive rate unfairness on the community crime data set of the conventional or fairness unaware model in blue and the fairness aware model in orange. And on the x-axis, we have the manipulation budget of the agents. And what we can see is that when the manipulation budget is 0, meaning that all the agents truthfully report, meaning we're just working on the standard true distribution, the fair model is in fact more fair. However, as this manipulation budget grows, meaning that the agents are able to have more effective or larger manipulations, we actually see that the fairness of the two models swaps. And at this moment, with respect to the manipulation budget, we are seeing a fairness reversal, meaning that the fair model is now, in fact, less fair than its fairness unaware counterpart. And kind of in the paper, one of our key observations is what causes some classifiers to exhibit fairness reversals. This is by no means a universal phenomenon. It happens in certain specific cases, and many of our results are about outlining those specific cases. And one of the key aspects that we find that contributes to fairness reversals is the way in which the fair model goes about achieving its fairness with respect to the conventional model. And so what we're saying here is if we look at these decision regions here, we have in the orange, we have, again, the fair model. In the blue, we have the fairness unaware model. And what we see is that the fair model is a lot more exclusive, meaning that it's positively classifying fewer agents than the conventional model. There are many agents that when we switch from the conventional model to the fair model, they lose positive classification. And we observe empirically and theoretically that this is precisely what leads to fairness reversals, is whether or not the fair classifier achieves its fairness through this kind of exclusive means. And here's just kind of another example in the law school data set. Here we see that there is, in fact, no fairness reversal. And if we plot the decision boundaries in 2 dimensions, we see that in this case, there's a lot more inclusion, meaning that the fair model is including many more examples than it's excluding. And we notice that in these types of examples, we do not observe fairness reversals. And we define this notion of selectivity in order to kind of get some theoretical results. And what you can see here is that the FAIR model, we say that the FAIR model is selective with respect to the conventional model if the positive region is a subset of the positive region of the conventional model. So what this would mean is that effectively fairness is being achieved purely through exclusion. There is no inclusion. We're not adding any additional positive examples in the FAIR model's decisions. And we have kind of a wide array of theorems in the paper that all kind of can be somewhat informally stated as fairness reversals occur when the FAIR model is more selective than the conventional model. And this is precisely the behavior that leads to fairness reversals. And we also observe both empirically and theoretically that these fairness reversals are accompanied by accuracy reversals. So if we recall before, the conventional model is effectively the most performative or highest accuracy model. And what we see then is that strategic agent behavior in these cases is leading to a complete swap of the functionality of both models. The FAIR model is no longer the most fair model, and the most performative model is no longer the most performative model. So we see kind of a functional swapping of these two models in what they end up doing. And just for time, I'm going to kind of skip this and go to the conclusion. So again, strategic agent behavior can lead to FAIR models becoming less fair than their fairness agnostic counterparts. Fairness reversals, again, are accompanied by accuracy reversals. And classifier selectivity plays a crucial role in both fairness and accuracy reversals. So thank you all very much for coming and listening. And if you'd like to check out the paper, it is Group Fair Classification with Strategic Agents. Thank you very much.
The next speaker is Brianna Richardson.
Thank you so much, everyone, for being here. My name is Brianna Richardson. I'm a PhD student at the University of Florida, and I'm here presenting a collaborative effort between colleagues at the University of Florida and IBM Research. So my agenda for today, I'm going to talk about the motivations behind our work, give some relevant background information, talk about our proposed bias mitigation solutions. We can see some of those results in action, and then end with conclusions and future work. So much of my motivations we probably already know. Machine learning is prolific. You can find it across the industries. And being so prolific, the impacts of machine learning, which are often biased, can impact the machine learning models that we use, and therefore impact the different domains in which we use those machine learning models. Responsible AI is a collection of efforts that have different objectives in reducing bias and fairness specifically, consists of diverse solutions to remedy bias. But despite the diverse size of the fairness solution space, you'll find that practitioners often don't use these tools in practice. So a number of works have studied practitioners and gathered their thoughts on algorithmic bias efforts. Practitioners voice concerns with complicated solutions, irrelevant strategies, and overly flexible types of manipulation that they simply aren't allowed to do in their domain. It is worth reiterating that the fairness research space is expansive. When surveying the bias detection space, Verma and Rubin found over 20 different bias detection methods. And then when surveying the bias mitigation space, Katana and Haas identified over 100 different bias mitigation methods. So I'll repeat, the fairness research space is very expansive. But despite the sheer quantity of solutions that exist, there persists gaps between fairness experts and machine learning practitioners. One of the many disconnects is the lack of explainability and transparency in fairness mitigation strategies. In order to bridge this gap, we decided to investigate the use of influence functions from robust statistics. Influence functions have been used in explainability research as a method to identify influential instances. We wondered if we could use these same methods to explain fairness metrics for practitioners. An influential instance is a point that, if deleted from the data set, would greatly impact the predictions of the model. The organic way to determine this is to remove a sample from the training subset, retrain the model, and see how the prediction changes before and after the deletion. Of course, this isn't practical with complex or large models, so that's where influence functions come in. They allow you to recompute model parameters to derive influence. You upweight the loss of a training sample by a very small amount epsilon, and then we can approximate the influence of a training point Z on a test point Z test using 2 loss gradients and a Hessian matrix. So here I show this equation for the influence of a training point Z on a test point Z test. This original work was done by Ko et al. In 2017, and it's been very influential for the interpretable ML space. Recent work by Satageri et al. Took this another level. This was recently presented in the NeurIPS conference. So they derived a formula for computing influence of a training point on an evaluation distribution ZT using a given group fairness metric M. By modifying the loss gradient in the original equation, which it's this loss gradient, they simply replace it with your standard group fairness metric. They're able to derive a new use case for influence functions. While they demonstrate that these group-based influence functions can be utilized to remove harmful or bad data, our work aimed to demonstrate that this formula can be used to create a family of mitigation methods that are transparent and cater to practitioner needs. In this work, we call this influential fairness. So we had 2 objectives behind our work. First, we wanted to better delineate the needs of practitioners by creating user profiles, and then we wanted to utilize influential fairness scores to design profile-catered mitigation methods. After a literature review through relevant works, specifically works that elicited feedback from practitioners, we were able to generate 4 different distinct profiles. We have our free-range practitioners who have complete access to the model and their training data. They have access to new data, and they're not limited by rules. You'll find that most mitigation methods are built with these practitioners in mind. They don't have limitations. We have our data-limited practitioners who have access to the model and the training data, but they don't have access to new data, or it's very, very expensive to get new data, and they're not limited by any rules or restrictions. You'll find protocol practitioners, which many practitioners feel like they're protocol practitioners in literature. Here they have access to the model and the training data. They have access to new data, but they're very limited by rules and regulations that they've placed on themselves or their institutions have placed on them. And then we have the auditing practitioner who has no access to the training data. They have black box access to the model, but they're trying to make things more fair. So our objective was to make mitigation methods for these 3 practitioners who often go unrecognized in the fairness solution space. So before I go introduce my mitigation methods, I want to be very clear about the stage in the ML pipeline where my mitigation methods exist. So my mitigation methods are our mitigation methods are post hoc methods. So once a model is generated and fairness performance is done on some evaluation subset, here we calculate those influential scores. We use a mitigation method we apply that mitigation method to our training subset, and then we just retrain the model. It's very simple. It was made simple on purpose for practitioners who don't have the history and complex fairness procedures that we all have. If they want to continue to get better outcomes for their fairness, they can do this iteratively as well. So we propose 5 different mitigation methods. They're designed to be understandable and very simple methods. Opponents are samples that have scores that indicate that they're bad for fairness, and then proponents are samples that have influence scores that signify that they could improve disparity or reduce disparity. So the 5 methods, there's removal, where you take opponents, take them out your training data. There's duplication, where there's duplication and addition, which are very similar. Duplication, you basically upweigh samples in the training data that are considered good. Addition, you find samples out from a external held out subset and you add them to your training data. There's relabeling, where you take your opponents, you change their label outcome, and then you change them within your training subset. And then there's inverted nearest neighbor duplication, where you identify your opponents, you locate the nearest inverted neighbor, and then you duplicate that neighbor. And so our objective was to see how these work, I guess, in the wild. So again, our objective was to build methods with practitioners in mind. So removal is a method that could work for free-range practitioners, but it won't work as well for other practitioners. Then duplication is a great method for duplication and relabeling are both good methods for data-limited practitioners, and addition method is promising for protocol and auditing practitioners. So we tested, sorry, that's gone, okay. So we did this on 3 different data sets with 4 different fairness metrics, and that's all that slide showed. And so we had 5 experimental inquiries that we were looking at. I won't go into all the results because we do not have time, but I'll talk about a couple of them. Are our ground truth scores valid? We basically iteratively removed opponents and proponents and looked at how the disparity changed. You can see that as you remove opponents, you get closer to 0 disparity. As you remove proponents, you get closer to, you get a higher disparity. And this was the case for all of our different scenarios that we were working with. Our second inquiry is, do we need to do an iterative? I showed in that graph how you can do it iteratively. Is that necessary? How large of a perturbation should you make to the training data? We basically found the point of diminishing returns, which is called the knee of the curve, and we decided to use that, and that produced really great results across our use cases. And then our last one is, how do these methods compare to existing methods? In short, they do really well. Here's our original model plotted on accuracy and disparity. Our purple methods are the ones that we proposed. The orange ones are the pre-existing ones. Our objective is to get here where we maintain accuracy and reduce disparity. And our methods do pretty well. Each use case was different, but across the board, our methods did pretty well. So in conclusion, our influential fairness methods are entirely human in the loop. Practitioners control the metrics that they optimize, the techniques they mitigate with, and the size of their perturbations, which gives them complete control, which is what they asked for. Our future work is we want to apply this methodology to more complex models. We just use logistic regression models, but we want to engage with more complex models where we might have to use Hessian estimates. We want to look at robustness scores, look at second-order influential fairness, and then obviously our focus is practitioners. So get this out in the real wild and see how practitioners engage with this. Thank you so much.
Great. The next speaker is Catherine Cacho.
Okay. Hi, everyone. My name is Kathleen Cashel. I'm a PhD student at WPI, and I'm going to be presenting joint work with my advisor, Elke Rudensteiner. I'm going to begin by talking about rank aggregation, which is the problem of combining voter preferences, which are expressed as rankings, into a consensus ranking. So in the slide, you see we have 8 candidates and 3 voters. And so in the context of rank aggregation, each voter provides a ranking over all the candidates, and the objective of the problem is to find one single consensus ranking that more or less represents the preferences of all the voters. This problem has many applications in social choice and information retrieval. So specifically in social choice, anytime you're making a collective decision as a group of people together for things like award determination, where reviewers look at different applicants to determine who receives a scholarship, and in information retrieval for things like combining ranking models and providing group recommendations. In all of these contexts, the final consensus ranking that is produced can have really severe consequences for the candidates being ranked. So specifically, when we think about bias in terms of candidates, in the context of rank aggregation, if we have different groups of candidates that are being ranked, and our voters themselves may have some sort of implicit or explicit bias, even if the voters aren't severely biased, that bias can get aggregated into that final consensus ranking when you're using conventional methods. And so that can have consequential outcomes for those candidates being ranked. An additional thing to consider in terms of that final consensus ranking is that how it is used is that the decision maker's attention is concentrated at the top of that ranking. So it's more important to be at the top of the ranking than at the bottom, and so that becomes important when we think about mitigating bias. So our objective in this work is to basically come up with a fair consensus ranking. And so this is a multi-objective problem. And so the first thing we want to do is achieve candidate fairness, and we want that to incorporate this and address this issue of position bias. And then we also want to combine voter preferences. Specifically, we want to maximize what I'm going to call preference representation. And so that's the idea that the rankings of the voters are expressed in the final ranking. So in terms of related consensus ranking approaches, there's a long line of work in social choice where rank aggregation is referred to as voting. And there are many of these rules that are used to combine voter preferences, and they don't have any consideration for the candidates that are being ranked. Of note is Khamenei, which is particularly popular since it satisfies a number of social choice axioms. Recently, there has been work integrating candidate fairness into Khamenei specifically. So there's the pairwise fair Khamenei methodology, and so that incorporates pairwise ranked fairness into the Khamenei optimization problem. But this does not account for this issue of position bias that we'll see later on. Additionally, there's this method rank aggregation p-fairness, which selects a single voter's a single voter's preference ranking, and then re-ranks it to be fair. And so in this case, it's using a representational form of fairness, and so that also doesn't kind of factor in this position bias issue. So in this work, we're setting out to work across these 3 columns of combining voter preferences addressing candidate fairness in the presence of position bias. In the paper, we formulate the fair exposure Khamenei rank aggregation problem. So at a very high level, given a set of voter preferences, the goal is to find a ranking such that there's a minimum level of fairness. And so specifically, we're using the fairness of exposure notion, which addresses candidate bias in terms of position bias. Candidate fairness in terms of position bias. And then the second objective is to maximize consensus accuracy, which is a metric we introduced in the paper that measures the amount of preference representation in the consensus ranking compared to the voter preferences. And so in a nutshell, what we're trying to do is constrain fairness and maximize voter preference representation. So in the paper, we present 2 methods for solving this problem. Both of them are fairness tunable, which means that they take in a given desired minimum fairness level and allow you to achieve a consensus ranking with that amount of fairness. So the first is exposure parity in Khamenei. And so this is an integer program that is optimal, and it ensures that candidate fairness is found in the Khamenei consensus ranking. And so in the paper, we explain how we reformulate the listwise fairness of exposure notion to integrate into the pairwise Khamenei integer program. The second method we propose is exposure parity and rank aggregation. And so this is a post-processing strategy. So it first finds a traditional consensus ranking, and then it uses a method to adjust that consensus ranking to satisfy fairness of exposure. And in the paper, we have some proofs showing how this is done so as to minimally decrease the consensus accuracy. Additionally, in our experiments, we study kind of this approach of post-processing a conventional consensus ranking by studying how this method performs with a number of voting rules. So turning to our experiments, we compare these 2 methods against the prior methods that were mentioned, and we see that because these methods are fairness tunable, you're able to get the desired level of fairness. What's interesting is when we compare it against consensus ranking methods that have alternate fairness objectives, we find that if your objective is fairness of exposure and you're using a different fair ranking objective, you can actually, in the context of consensus ranking, end up in a more unfair consensus ranking than had you just used the standard Kameni rule. So put another way, if you don't pick the fairness properly, you can end up in a worse place than had you not done any intervention at all. Additionally, we would provide a number of takeaways using the Mallows statistical model. So this is a model that allows us to study how under different conditions of voter agreement, the methods perform. And so what you're seeing here is a heat map where every box represents what's called a preference profile or a set of voter preferences. And so on the y-axis, what is happening is the fairness of the voters is increasing. And on the x-axis, what is happening is those voters are agreeing more and more with one another. So we see that our methods are able to kind of, under all of these circumstances, come up with a fair consensus ranking. But it's interesting to note the cases that we describe in the paper when using a traditional voting rule also gets you to a fair consensus ranking. I think perhaps intuitively, one of the main takeaways is that if you have voters that are in agreement and not biased, you're more likely to end up with a fair consensus ranking. So in conclusion, we introduce the new fair exposure Kameni rank aggregation problem and provide two methods for solving it. Finally, I'd like to note an interesting kind of limitation of this work because it is such a deterministic problem, and it is really multi-objective. So we have these competing fairness versus preference representation objectives. So we're not able to make statements like, you can get a fair consensus ranking and really great preference representation, because it completely comes down to the specific problem you're solving at hand. Interestingly to note, in social choice, this concept of preference representation is referred to as fairness itself. And so that refers to voter fairness, versus what we're trying to do in this work is think about candidate fairness. Thank you so much for listening. If you have questions, feel free to talk to me after.
Final presentation in this session is from Jose Alvarez on domain adaptive decision trees. And after this presentation, we will welcome all the presenters back on the stage, and we'll take some questions. If you have questions, you can line up at the mic over there.
All right. Good afternoon, everybody. So my name is Jose Manuel Alvarez. I'm a PhD student at Scuola Normale Superiore in Pisa, Italy. And today I'll be presenting our work on domain adaptive decision trees, where we propose an in-processing method for decision tree learning that incorporates a domain adaptation problem. And as the title suggests, under this intervention we propose, we show some interesting improvements in accuracy and fairness of the trained model. This is joint work with my co-author, Kristen Scott from KU Leuven, who's also today here with us, as well as with Tina Berendt and Salvatore Ruggeri. So a bit of background, say, from the title, you can guess there are two main pillars to this work, and one being the domain adaptive part, and the other one being the decision tree part. So by domain adaptive, we're talking about the domain adaptation problem. So at a high level, domain adaptation is a field not only restricted to machine learning, but that handles problems where we figure out patterns or learn a certain pattern from one domain, i.e. context or scenario, and we try to see if we can apply those patterns into a new context that is not necessarily related 100% with the previous one. So it also happens to humans, so at a high level or a human level, say probably all of you can drive fairly well in Chicago or in the United States, but could you drive as well, say, in Florence or Pisa, Italy, no? So it's still about driving, but the domain kind of implies different behavior. So in the machine learning sense, we can conceive it as the information that we have available for training is not representative of the intended population of the model. So more formally, we talk about a source domain, so say the training data, versus a target domain, so the intended population or test data, and that their distributions meaning they're both the attribute space and the label space. There's something about it that doesn't add up or match exactly as we have here in the equation. What's the issue with this is we train the model on the source domain and then deploy it on the target domain. Then this deployed model happens to be biased with its intended target. So this can lead to poor model performance and potentially to an unfair model when deployed. Now, why focus on decision trees, especially this year with the whole deep learning hype? Well, for those who are not familiar with decision trees, we have an example there on the slide, but I assume most people here know what they are. Well, these models are extremely valuable still, and there's a bit like a decision tree renaissance according to people like Cynthia Rudin. So they're popular both among practitioners and academics. They're competitive when we're talking at least about tabular data, performing as well or even better than most of these complex models, and they're inherently interpretable, at least relative to the complex models. And then given this characteristics of decision trees, we would argue that they're quite suitable for the incoming regulation. Well, I should add the existing regulation because the EUI Act got approved today. But then they're very attractive for people who decide to do automated decision making, for example. And then additionally, they have some inherent properties that make them quite suitable for the domain adaptation problem. So hence why we decided to focus on them. Now, before I get into the details, I have to say it's a bit of a dense paper, so I will butcher it a bit to get the main message across. So feel free to check the paper, please do. So let's get a bit into the details. So of course, domain adaptation, you can describe it in many ways, like how exactly are these two populations diverging. So here we focus on covariate shift, which formally just states, well, it's based on two conditions. The first one is that the conditional distribution across the domains is the same, but the distribution of the attributes changes. So why do we focus on this one? Because in practice, this means that we require information about the target attribute space, but not necessarily about the target label. So this is quite, in practice, a realistic assumption because, say, if you're a new store targeting a new population of clients, you only, say, have access to the attribute space, but you have no information about their consumption habits because they have never consumed in your store before. So this describes a very common setting that you would find in deployment. And then why the decision tree? So there are many ways to grow a decision tree, one of them being the information gain split, which is based on information theory notions. And we have here the information gain split, but what is very relevant here to understand is that, this is a way of growing a tree where for a current path, i.e. where you're going through the current node and combinations of nodes of the tree, you try to find the attribute X and a threshold that would maximize the information value gained by partitioning the data. So what does it mean? That we try to find a split that partitions the data in a way that you gain more information about the data at hand. So all that we need to kind of know from this slide is that in this calculation, two probabilities are involved, the ones that we have on the slide. And because these probabilities are also involved in the standard decision tree learning problem, you're working with the training data only, say, so only the source population. So that means this IG, which is a random variable because of the calculation, approximates is distributed based on the source population. So in the domain adaptation problem, what we're interested is for this IG to approximate the target population as much as possible. So that also means that it's in terms of in-processing, it means that we need to estimate our probabilities somehow with some information for the target population. So now here we put one example, what we call the embedding target domain knowledge, and I'm sure you're going to have a lot of questions about this slide maybe after the talk because it has a lot of content in it, but it's just to show how we do this for one of these probabilities, the probability that X equals the threshold given the current path. And essentially what we propose in our framework is if you have access to some information on the target domain, you can try to incorporate it while learning the tree. So then the estimated probability that you have here on the screen is what you want is for it to approximate as much as possible to the target population. And you try to combine what you have of the source population and the little information you have of the target population. So this is by all means implementation specific because it's a matter of how much information on the target domain you have at hand, what type of information you have, and how, say, for example, how confident are you of this information. So this is where this alpha parameter comes in. So then in experiments, because then what we decided to do, we have this framework. Let's see if it works. I mean, obviously it did work, but so the idea, we went with the folks tables, and we focus on the public coverage task where we're trying to predict low income for an individual, whether it's covered by public health coverage. And then the domain adaptation problem is we have, say, data on one state, and then we want to train this model and deploy it on another state, knowing that maybe these two states are not, one is not representative of the other. So maybe something like Texas and California, maybe. And then the question is how much target domain information. So if you can think about it, it's like as a spectrum. So you have, in one case, is the no target domain knowledge, which is your standard setting. I only have access to Texan information. I train my model there, and I deploy it in California, and we see what happens. And then the ideal case is the target-to-target baseline, meaning in a hypothetical case, I would have access to Californian data, so I would not need the Texan data to start with. I would just train it in California. And then everything in between is a domain adaptive problem. So how does that, and of course we frame it in terms of full target domain knowledge and partial target domain knowledge, but because we're in the covariate shift scenario, it's a statement on how much knowledge we have on the attribute space. So in this case, we have access to the full 6 attributes or only some of them. And if you look at it in terms of the spectrum of the covariant shift problem, you want to ideally be on the green smiley face, not on the red sad face, but then everything in between is the domain adapted decision tree problem. So very quickly, because I'm running out of time, what we do here say that the x-axis is a measure of the validity of the covariate shift assumption, and I'm happy to discuss the specifics, but essentially a 0 distance implies the scenario of the covariate shift. And then on the y-axis, we have a measure on relative accuracy, and by relative accuracy, what would the model performance be moving away from this not so ideal no domain knowledge, no target domain knowledge, and approximating the idealized target to target. And then, so you see the improvement in accuracy. And we also do the same for the fairness as measured by demographic parity and equal opportunity. So in terms of conclusion, so this is the first attempt, as far as we know, on doing the domain adaptive problem for the specific to decision trees. We show an improvement in accuracy with respect to the standard decision tree and some promising results on fairness. We emphasize that this is not intended as a replacement for collecting improved data sets. And there are a lot of future directions, as this also being an initial attempt. So feel free to read the paper, find some flaws, and then improve on it. And thank you very much.
Speakers can come back on stage, and if you have questions, you can go to the mic and ask your questions. Great, you can go ahead.
Okay, I have a question for Andrew with the group fairness with strategic agents work. So say I have the following setup. I have a fair classifier, and there are 2 groups. One is advantaged, the other one is disadvantaged. And the fair classifier prefers people from the disadvantaged group to get some kind of fairness. Now, the people are strategic, and they recognize that the classifier is preferring people from the disadvantaged group. So people from the advantaged group try to change their features to appear as disadvantaged. Now, if the manipulation budget is high enough, such that advantaged people can do so, is this kind of fairness reversal that you described unavoidable?
So it could potentially be unavoidable. I guess this is the case where the classifier is group aware. So in the paper, we look at both the case of group aware and group unaware classifiers, and we find that in the case that you're discussing, the group aware, it's far more common to see fairness reversals for almost precisely this reason, is that as soon as there's enough budget for the agents to lie about their group, we see almost like an immediate phase shift in the fairness, and it becomes significantly less fair. I don't know if it's unavoidable. I mean, I'm pretty sure that, there must exist a case where the classifier is group aware and there aren't fairness reversals. But I don't know, we don't have any specific results that are saying it is unavoidable if you consider groups, as where if you don't consider groups, then it's avoidable.
Okay, thanks.
Yeah.
I also have a question for Andrew, if I may ask. And another question after this, if no one wants to follow up. Cool. So I want to make sure that this is not just me looking at the pictures and, I don't know, mistaking correlation for causation. But it just seems to me that you have two regions colored by blue and orange with respect to the fairness aware and fairness unaware. And then it just seems to me that one of them is more regularly shaped, like convex maybe. And then the other one is sort of more not regularly shaped, and I was wondering if that has anything to do with what you mentioned as sort of the sensitivity, or what was the term that you used? The
selectivity?
Selectivity, yes.
Yeah, so we don't necessarily care so much about the shapes of the classifiers, but at least for our theoretical results, what we care about is that the positive decision region of the fair classifier is a subset of the positive decision region of the conventional classifier. And so when we have these kind of like very obtuse shapes, like the one that I showed on the law school data set, it's going to be easier for people to manipulate to be positively classified in those cases, because right, if you have all these kind of weird jagged regions, they only have to get into one of these jagged regions as opposed to something more spherical. But empirically, we would observe that maybe these kind of jagged regions enable people to get positively classified more easily, but it doesn't play a role in the selectivity.
Cool, awesome, thank you. I also have a question for the first paper. Oh, so sorry.
Thank you, sorry. Danny Shaman, Enroll Technology. I have a question for the paper about bias mitigation. The techniques you discussed were really focused on identifying like label errors and similar in training data, and the iterative process of improving those labels through training. However, it seems to me likely that if there are biased labels in the training data, that your testing data also has the same label mistakes. And I was wondering if your approach had any capacity to address those testing labels.
Yeah, so that's what is very difficult. So I proposed for, you notice that the duplication and addition were very similar. Addition is the identification of influential instances outside of your training data. Influence functions are based on training data. I was experimenting with using other trainers to identify negative or positively influential instances outside of the training data. So that's kind of where I deviated. And I have more work that kind of looks at like, how do we get influence scores for data that is not training data? Because there could be, like you said, ambiguities between, and that could account for some of the inaccuracies of some of those like relabeling mitigation methods. So yeah, that's a really great point. And I think, so as of now, the methods that I've used aren't great at looking at, especially when there's like huge distribution differences between like your training and your test data. So it's kind of hard to find those nuances. But if they're from the same distributions, they can do okay. Trying to identify the complexities of the influence functions. But yeah, I hope that answers your question.
Thank you.
Hi. So I had a question about the fairness in voting paper. So my main question concerns how voter preferences would shift given this, given knowledge of this system, because it would. I'm just trying to see the practical use cases of this, because in an actual situation where the voters are aware that their preferences will then be adjusted due to a bias, would they not then bias their results to counteract that? Because does this system assume that the bias correction method is hidden from the voters themselves?
The short answer is no. I mean, you raise a bunch of great questions that we're certainly starting to look at in follow-up work. I think the first thing is that voters don't often have to even be human, right? So that these could be preferences that are produced from a ranking model. So in that case, would their preferences change? Probably not. In terms of a voting model, potentially, yes. I think one way to view this whole kind of body of work is it's a tool in the toolkit. So maybe you don't adopt the method as saying this is the be-all, end-all consensus ranking. You calculate the consensus ranking as one might normally, and then you might compare it against a fair consensus ranking, and in a kind of collective decision-making process, have that discussion again. Does that make sense? But it's a great question. Thank you.
Thanks.
Well, we'll take one final question. Oh, no? Yeah, let's go.
I do have one question. I'm so sorry. I have a question for the first paper. So I guess due to my own ignorance of this literature, you defined, I guess, a fairness notion for streaming data, so online data. And I was wondering, is this sort of trade-off between fairness and accuracy like time agnostic, or is it dependent on the time index you're using? Like, does it hold, sorry.
So go ahead, yeah.
Oh, I was just going to say, does it hold when you take time to infinity, or is it more looking at like some bounded notion of time?
Yeah, like I said, most fairness notion right now is designed for static dataset. So like we said, like a static parity difference, which is a common use for group fairness. As we say, because they calculate at time t, but right now, like because this is streaming data, so the data will come in infinitive, they keep coming. So once it's coming, the total number of data will be changed. And the static parity difference is basically like, total number with like different sensitive attribute, you calculate the positive and negative. So once if the size is increased, so static parity difference will be changed. And this is important you should to consider, like because the time t and the time t minus 1, because once it keep coming, there will be a change in influence, because they might become like more like a positive for male, and they come to like in next time it's just like all the data is like a negative female. So that's how the change the static parity difference. So we should consider, like I said, the continuous static parity difference. We come some like t minus 1 and plus like the time t, what's the static parity difference. And the important control is lambda, which is like you want to pay more attention on the right now, I mean time t data, or like you want to more like in the history, which is t minus 1.
Cool, thank you.
Right,